All right, so let's work on. So this is the fourth video in our exploration of Sylow's theorem. Right. So this is video 4 in our exploration of Sylow's theorem, and one thing we've come to is, I mean, we know what the theorem is saying. It's telling us if we have a finite group of order G, and the order of G equals to p to the alpha times m, where p and m are relatively prime, then we're saying this must necessarily imply that we are guaranteed there exists some subgroup h of G such that order of h equals to p to the alpha, right? P is prime here, and alpha is being taken to be greater than or equal to 0, some natural number. Alright, so notice, so this is what we've been trying to prove for a while back, and so far we've been deep in the jungle, but we did come up with an approach before, and let's see if we can maybe explore it again today, right? So let's see if we can continue with our approach. The idea was, actually forgotten the approach. Yeah, what was it again? Right, so here's kind of what we're thinking of as the big picture of a potential strategy. So strategy was, let's take some h, let's take some h subgroup of G, right? Now if we can show that for this h subgroup of G, it's true that the order of h is relatively prime to the order of m. That is, if the GCD of order of h and m equals to 1, right? Then what does that tell us? Given that we know that the order of h must divide the order of the group itself, which actually happens to be p to the alpha times m, right? What can we conclude from here? Can we conclude that if order of h is relatively prime to m and order of h divides order of G, can we assume that the order of h equals to p to the theta, right? Where theta is some natural number, right? With the Are we saying that theta has to be less than or equal to alpha, less than or equal to 1? So our strategy was, suppose we prove that order of h is relatively prime to order of m, and that there exists some subgroup h such that the order of h is relatively prime to m, right? And doesn't that mean that order of h equals to p to the theta? And suppose we are also able to prove that the order of h is not less than p to the alpha, right? Wouldn't we have then guaranteed that the only option is the order of h has to be p to the theta, p to the alpha then, right? So this was the strategy. Um, so the first question is, how do we know we can find a subgroup h of G such that the order of h is relatively prime to m? Right? That is not so clear that we're able to do that. So let's see. Uh, why is it that if the order of the group equals to p to the alpha times m, then there exists some h subgroup of G such that the GCD of the order of h and m equals to 1, right? Order of h and m are relatively prime, right? Well, why is that true? Why are we guaranteed of this, right? And so we're saying, well, maybe one strategy to use is, well, suppose that we are not guaranteed of this. Suppose that there actually exists, for order of G equals to p to the alpha times m, right? Um, let's say that there does not exist, right? Let's say that there does not exist some subgroup h of G such that order of h, GCD of order of h and m equals to 1, right? How else can we write it instead of saying that does not exist? Can we say that for all h subgroup of G, uh, it is true that it is true it is true that the GCD of order of h and m does not equal to 1, right? But what does it mean for the order of a group to not equal to 1? Doesn't it mean that order of h and m have some factor in common other than m, right? So are we saying here that the order of h has to equal to p to the theta, some theta power of p times some l, where l, since order of h is not relatively prime to m, and we're saying that then l has to be such that l divides m, right? There has to be some factor of m, and l is not equal to 1. It's non-trivial, right? We said the GCD doesn't have to be 1. So if this is what we're saying, that the order of h has to equal to p to the theta times some l, right? Well, can't we apply our kind of assumption again here? That is, well, now is it possible for the if order of h equals to p to the theta times l, right? Is it possible that there exists some m subgroup of h such that the GCD of m and l, right? GCD of m and l equals to 1, right? Is it possible? Suppose this is true, that there is some m subgroup of h such that the GCD of the order of m and l, right, actually equals to 1, right? What is that telling us? Well, this is supposed to be l. Just don't know why we decided to write it in this cool way here, but yeah, that's what we have. So suppose that there exists such a subgroup, right? Well, what can we say? If there exists a subgroup of m such that order of m is relatively prime to L, and we're saying then that the order, since m is a subgroup of h and h is a subgroup of g, and we're saying that the order of m, right, must also divide the order of g, right? Right. So wait, this is actually leading to confusion now. All right. Sure, we have some subgroup m of h, m of g such that order of m, I mean order of m, we're saying Lagrange's theorem tells us order of m must divide the order of g. Fine, but oh, actually, maybe we don't need to proceed this way. But here's what we can say for sure. If well, let's see if you agree that we can say it for sure. So if we know that there exists some subgroup m of h such that order of m and GCD of order of m and l equals to the identity, right? If we know that to be true, can't we conclude the following? Can't we say that, well, if order of m has nothing in common with l, aren't we saying that since m is a subgroup of h, and Lagrange's theorem tells us that the order of m divides the order of h, right? Aren't we saying that this means that order of m has to equal to p to the j, right? Times it can't have any element in common with L, so there can't be some factor of L here, right? But if order of m equals to p to the j, and m is a subgroup of h, which is a subgroup of g, right? And we're saying that, well, and haven't we found a subgroup m of g then, such that the order of m equals to p to the j? If the order of m equals to p to the j, and we're saying that uh, order of m is strictly relatively prime to what we started with, m. Oh shit, we use the same symbol. So this is big M, right? Relatively prime to little m was supposed to be right. So we started with a group of order p to the alpha times little m, right? P to the alpha times little m, and we picked that. We said that, look, we pick a subgroup h of g, and the order of h and little m is gonna, GCD is gonna give us 1, right? Or actually, we're assuming that it can't give us 1. That for no subgroup h of m of g can we ever have order of h, GCD of order of h and little m giving us 1, right? But now we found some subgroup m of g, right? Subgroup m of g whose order is p to the j, and order of big M. So doesn't that mean that the order of big M, since we said before that P is relatively prime to M, little m, if P is relatively prime to little m, right, how can P to the J, isn't P to the J also relatively prime to what? Isn't P to the J also relatively prime to M? If that's the case, and order of M equals to P to the J, and we're saying that the order of M is relatively prime to little m, so isn't that giving us 1 as well? But isn't this a contradiction to the assumption that we made that for every subgroup of, there is no subgroup of G such that the order of that the GCD of the order of that subgroup with little m gives us 1, right? So what we're saying here is that, and we're saying here that perhaps that our assumption was wrong to assume that for, right? So again, we started from G, we obtained a subgroup H, and now from H we obtained a subgroup M. We said that the order of M was P to the theta times some L, L not equal to 1, and we assumed that there actually exists some that actually this was H, sorry. Right, so we came up with the following, that there's some subgroup H of G and the order of H equals to P to the theta times L. L does not equal to 1, and we said that look, if there exists some subgroup M of P to the theta, sorry, of H, if there exists some subgroup M of H such that the order of M is relatively prime to L, then that also means that we found a subgroup of G that's relatively prime to M, whose order is relatively prime to M, but we said that can't happen. So what are we saying here? We're saying that, look, there does not exist a subgroup, let's use a different letter than M. There does not exist a subgroup L of H, right, such that order of L, okay, such that order of L, GCD of order of L and, did we use the same symbol again? God damn it. Okay. Let's use something else. What letter makes you happy? Let's pick Q. Oh, why not? Q. Let's not confuse with the rationals. All the letters are taken out. Okay, so, and we're saying that there exists some Q then, such that order of Q, right, such that GCD of, and we're saying that there does not exist a subgroup Q of H such that order of Q, GCD of the order of Q and L, right, does not equal to 1, right? But what does this mean? Weren't we in a similar situation before where we had a group of order P to the alpha times M? And we saw that, well, if we have a group of order P to the alpha times M and there is no subgroup whose order is relatively prime to M, then that means that there must exist some other subgroup. In this case, we had said H, such that order of H is P to the theta times L. So can we conclude then there must exist some subgroup N of H such that order of N equals to P to the J perhaps times some K, where K does not divide L, okay? K does not divide L, right? And J is some power less than or equal to theta. So if this is the case, right, and we're just reducing powers, so we started from P to the alpha times M, then we found a subgroup here of order, a subgroup here of order P to the theta times L, right? And then we found another subgroup of order P to the J times L, right? So times some K, and then we just kept going on, right? Oh, geez, what did we write? Oh, Jesus Christ. All right. So please remember this reduction, because next time we'll start from here. Unfortunately, today, not sure if it's unfortunate, but today we don't have as much time, so, right. So this is really what we have now, P to the alpha times M, right? And we seem to be reducing, but it's possible, see the less than or equal to, it's possible that, is it possible that, look, the subgroup H that we picked some subgroup H of G, right? H of G, but, and we said that the order of H has to equal to P to the theta times L, right? Where L does not, where L divides M and L does not equal to 1. So what's stopping L from being equal to M, right? That's the question. Because, right, okay, maybe before we even go to why this is important, if these kind of inequalities were less, if the order of G was actually P to the alpha times M, okay, we know that, but the order of H was strictly, P to the theta times L was strictly less than P to the alpha times M, and P to the I times K was strictly less, then perhaps we could actually end up reducing, since the value of the divisors of M is reducing, L is a proper divisor of M, we're thinking, and K is a proper divisor of, let's say K is a proper divisor of L. If this is happening, then aren't we eventually maybe perhaps going to convert to just some P to the 2 or something, P to the J, right? So that we found some subgroup S of G such that order of S equals to P to the J, right? Oh, and wouldn't this lead us to a contradiction then, right? If we're getting a contradiction, right? If we're getting a contradiction, and we're saying that our assumption before, right, that there does not exist a subgroup such that the order of the subgroup is relatively prime to M is bogus. And so which will tell us there must exist a subgroup that's relatively prime to M, right? And maybe we'll be able to proceed from there. But the key is this, and so next time we'll not like really rederive this, but we'll start from around this point. That is, if we assume that there's always a subgroup, that all subgroups always have a non-identity factor in common with M. If we assume that, then okay, is this chain of subgroups that we generate, P to the alpha times M, P to the theta times L, P to the I times K, is this chain of subgroups proper subgroups, or are they actually the subgroup? That is P to the theta times L actually, can it be equal, let's say, to P to the alpha times M, right? Because if they're equal, then this reduction may not be a reduction. We may just be writing P to the alpha times M differently, as P to the theta times L, P to the I times K, but it's really the same thing. So, yeah, we just run out of time. See if this strategy is convincing or not. So, this is an exploration, which means we don't know. We're trying to figure things out. So we don't know whether this reduction works or not, but next time we'll hopefully be able to know definitively. If it works, great. If it doesn't work, great. That means we can legitimately abandon this strategy and think up a new one, right? So, right, thank you very much for watching this video, and have a relentless week. Bye.